All right, so again, we're going to learn how to read schematics right now. So the schematic diagrams represent an electronic circuit in symbolic form. Okay, so the schematic doesn't necessarily depict the actual physical arrangements of components, but it's going to be more like a drawing, and the board physical components as well as the layout may look very different. So you really are not going to necessarily recognize a board once you see a schematic. But once you start understanding how the wiring is on the schematic, then the board itself will make sense. So you can't also, it's very hard, especially on complex boards, to understand a board without a schematic. So if ever somebody gives you a board and says, here, figure this out or do something with it, the first thing you should ask is, where's the schematic? And that's going to then tell you how you should read and troubleshoot that electronic device. Some designs are proprietary, so sometimes it can be hard to get a schematic, but try to get that. So this is a schematic. This schematic is of something called the SCEDARSAT. The SCEDARSAT is a board that you will be assembling next week. So this is the actual schematic that you'll use for that. And so this probably looks very odd to a lot of people who has never seen a schematic before, but we're going to go through all these components. So the important parts of it that I'll point out are normally there's kind of just a page that the schematic is on. And then you'll see a title block at the bottom and you'll have a name on that. There's somebody that made the schematic. And then there's typically a date. You can see this is a pretty old schematic. And there also will be a revision history. So that's important if somebody makes any changes to these. And then usually you'll say like page 1 of 1 or 1 of 5 or whatever, at least you know how many schematics are with that design. Other times you might see things like this. This is more about how to read this is a device that we're going to be looking at as a transistor. So this is a little bit more of a physical representation of what the pins would look like to this device right here that we're going to be talking about in a little bit. And then there might be some other notes on here as well. And I like, when I make a schematic, I try to label as much as I can. So that way, whoever's looking at the schematic can understand understand as much as they can of the part without having to spend too much time on the data sheet. That is what the manufacturer provides for all of these different parts. So having all these pins nicely labeled and what values these components are is really critical when you make a schematic. All right. So let's just start. So first off, you saw a lot of lines here, and these are all wires. So literally physical connections touching the components, those different devices. Okay. And whenever you have two wires intersecting, that can be connected wires. And it's kind of odd here. They have this tells me for sure that B is intersecting this top wire, but then it's, to me, a little unclear on A, but this wire does end there at that, this is ending at this wire. So that's typically connected. On here, whenever you see all of these wires connected, C is definitely connected. And then D, you can see that it kind of skips over the wire. This is not so commonly used anymore, but if you do see something like that, it's nice because it tells you that for sure D is not connected to this wire, to the perpendicular wire. And E is really, we're not sure what's happening there. So sometimes that could be connected or not. So if you get confused about that, you know, especially if you're making a schematic, you need to make it clear how the wires are supposed to actually connect. So for the schematic symbols, or to continue on with the symbols, these are different types of power sources you're going to see. So this indicates a battery, and there's typically a plus terminal. Sometimes you'll see a negative, sometimes you'll just see a plus. And sometimes you don't see it at all. And that's what this is telling you, is that by convention, the longer horizontal line represents the positive terminal. The AC source is here. So it kind of looks like a sine wave. And you notice that there's not a polarity on it. And then we have a DC source, and that does have a polarity. So there is a plus and a minus that you need to be aware of. And that's just like if you have a 9-volt battery or any battery, and you've ever gone to plug it into your remote control or whatever, that you would see that there's like a plus and minus sign. That's kind of the way to think of that. And whenever you use a power supply as well, there's a positive terminal and a ground. So I'm showing here, this is ground. Ground is, remember, just a reference in the schematic that flows back to the original source. Okay, so to continue talking about grounds, this is usually considered an earth ground. Okay, and so when I say earth ground, what is that? So on your plug, wall plug, you have that bottom socket, the pin, that actually goes to an earth ground. And so it's really a conductor driven into the soil, okay? Then we have this little triangle that typically means a circuit common. So that's just a ground on a schematic. And a lot of times you'll have that for digital grounds, say, or analog grounds. If you have two different, if you have a schematic or a board that has two of those, you would denote those differently sometimes. There's a lot of different schemes with that. And then this is what we call a chassis ground. And so the chassis ground is typically the ground of it's the connection of the metal of the enclosure of a system. So for example, maybe you have I don't know, one of your devices for your TV or something, right? A lot of times that ground that is part of the metal enclosure is actually the chassis ground. And a lot of times these grounds, depending on the circuit, can actually all be connected somewhere. But a lot of times, especially with sensitive electronics, we want to keep these things isolated. And in particular, that earth ground from your common ground that's on your circuit. So just keep that in mind. So typically on our circuits that we're going to be using, we'll always have this sort of circuit common and not the earth ground. So moving on, Josh told you a little bit last time about resistors and capacitors, and I don't know if I think some of these symbols were on there, but this is the typical schematic symbol for a resistor. Okay, and then you have different types though. There are some resistors that can be adjusted, such as a potentiometer. And you can often see signs like this, but often see more common is this one over here with the arrow going through it. Okay, and that just tells you that in that circuit, that resistance can change by some mechanism. And usually it's like a small set screw that you can change it, but there's different ways. So the capacitors, these are all capacitors on the bottom, and there's so Josh probably mentioned it to you that some capacitors are polarized and some are not polarized. Okay, so when they're unpolarized, that means that you can put them in whatever orientation onto the board whenever you're actually putting the components in, as we'll see later. You can put them in whatever direction. But these polarized capacitors, which are typically electrolytic and sometimes tantalum capacitors, there is a positive lead. And so you need to denote that on the schematic, as well as we're going to be paying attention to that whenever we're doing soldering. And these adjustable capacitors, I haven't used these very often, but apparently that's the symbol for it. So if you do see it, it just means that it's kind of like the potentiometer where you can change the capacitance with some kind of mechanism. So for the schematic, or for the inductors and transformers, these are other devices that you might see. Inductors often are used for filtering, but they're also used as transformers, which is kind of right here when you're changing voltage, typically AC voltage, to different values. But these are all the symbols for this. So I'll just kind of have this up here that you might see. But typically it's a fixed inductor in henries, like microhenries. It's typically this one. So diodes, this is the symbol for it. So this is also one of those that's polarized, and it's really important to pay attention to whenever you're connecting this on a board. So the negative side is the one with the line on it. We call that cathode. And then the positive side is here. So the way I kind of remember it is, I think that like cats are sometimes mischievous. So like cathode, and then it's the negative, the bar. It looks like a negative sign. That's just my way of remembering it. You might have a better one. So If you do, you can share it in the chat. So otherwise, so this is the standard diode that you'll see. And then we also have the light emitting diode, so the LED. So this is like what is on your phone whenever you get a message and it lights up, you know, or on your Xbox to let you know that you've got it powered on, or whatever people use these days for video game consoles. So we'll be using those a lot, and these are really helpful, specifically so we can tell, you know, the status of something. But if it doesn't work, that probably means you have it in backwards. And then the Zener diode is a special diode as well. And that is used sometimes for like voltage regulation. It permits current to flow in either a forward or a reverse direction. So you can use it as like a normal diode, but then it also can flow in reverse direction without causing a lot of damage to it. It's meant to do that. So those are probably not going to be too commonly used for this class. And then this variable capacitance diode, I have actually not used one of those, so not very common at all. So yes, let's keep moving. The transistors. So these are showing two different types of transistors. So you can kind of think of both the bipolar NPN junction transistors, or the PNP versions, as well as what we're calling the MOSFET or field effect transistors. These can be used as switches, but also amplifying circuits. So the important thing is the bipolar one is a current device. So meaning that to turn it on, you simply start driving a current through the gate. So this is called the gate over here. And then as a result, the collector current IC will start to increase depending on the current of the gate. Whereas a MOSFET, these are voltage control devices. So to turn it on, you increase the voltage on the gate. And when this voltage is above a defined value, the threshold voltage, then you can, the device starts turning on. And so when I'm saying things are turning on, it's basically when you first hook this up without the gate being turned on, this is like an open circuit right here. But once you start applying current for these devices or a voltage for this device, then these will basically become a short, and you're shorting the top to the bottom. So that's kind of the simple way to look at it. So when you see it, when I see these, I always think of switch. But also they're important in op-amp circuits, so it starts to become more complicated with the currents and things whenever you if you see a lot of them on a schematic, it's more complicated than just a switch usually. Okay. So that's the main thing. You also should note the NPN versus the PNP. So the bipolar, the reason why it's called that is because it has two different types of carriers that contribute to the current. There's the electrons and the holes, and that has to do, the NPN is how the semiconductor is doped with, I'll just leave it at that for now. You can look it up more if you are interested in it. And so the most common one you'll see are these NPNs. The way that I remember this is also like a little trick, is not pointing in. So that's how I remember that one. The PNPs, oftentimes you'll see them flipped up from this. So this is a little bit different configuration, but there are reasons to use one or the other. Again, the most common one is the NPN, but sometimes you may have a reason to use the PNP. So if you start getting into more complex designs, you might want to spend some time looking that up. All right. So, and then the MOSFET, it's metal oxide semiconductor field effect transistor. That's the full name for it. But they're called unipolar devices because it only has one carrier. So the N is the electrons, the P is the holes. So again, feel free to look it up. They have some really cool videos out there on how these things work. And once you kind of understand the diode with the PN junction, because that's how diodes are made, then you can move into these other devices where they're becoming more complex, as well as how the semiconductors are doped, which is pretty interesting. So the schematic symbols, these are op amps. You'll be getting more into these later as the class goes on. And I think Josh went over this the last lecture. But then you also have like logic gates. So the and OR gates are some that maybe people are familiar with. And this is very similar if you're doing programming and you've used like, you know, the and symbols, OR symbols, very, very much the same idea. But it's just applied in logic. So you can do a lot of things with this. And then of course the not and, so it's got that little bubble right there. And then the nor, not or. And then a buffer, these are really important too that you'll see. Sometimes it's good to have a buffer with electronic circuits, and that's mainly because say that you have signals coming in from the outside world. So you have, say you've designed a board and somebody is going to use it, and you want to protect your electronics that are maybe like your microcontroller, or you have an embedded processor or FPGA, then it's really great to like use buffers to protect those more sensitive circuits. And so that's just one of the many reasons why you might have a buffer. And then you can have inverting, just meaning that it's going to invert the signal. But when you see this is just what I call follow through. That means that the same signal is on the input is going to be on the output. And then this would just be switched in polarity. So those are different things. The op amp, of course, is also important here because it is polarized with the, so I will say the signal input, it matters. It has a negative and a positive that you need to make sure you pay attention to. So, but whenever we install the device, you're going to see that these are typically full IC chips. So it's not like a capacitor or diode where it's going to have a plus and minus indicating this whenever we see it in the physical form. Switches, relays. So there's, this is literally what it says. It's a physical switch. So it's either connected or it's open. And you'll see here these single pole, single throw switches. This is a double pole, double throw. So the poles have to do with how you command it. Kind of like it's showing this here. There's coils within there that, and depending on the outputs, that's where you're going to see different types of poles. But in the single pole, single throw, then you just have like one switch. And when you get a double throw, that means there's two outputs. So in this one, you can see that the switch is open or it's closed. That's the only options. There's no connection or connected. In this one, you can switch it between this output and this output. So you always are connected here, except when it's in the middle of switching. Okay. And then when you get this double pole, single throw, that means that we're still, the single throw is just the open and close on both of these. But now on the same relay package, you'll have two inputs. Okay. And then this is the double pole, double throw. So now I have two inputs. Now I have four outputs. Okay. Well, two on each of the inputs. So why would you use, say this double pole, double throw? So there's a few reasons. Sometimes you can get more current out of these relays will be rated for some current. That's something that you should be very aware of so you don't damage the device. And so sometimes people use this to double up in order to get more current across the contacts. I like to use these when I design things as, I use one of these as a status bit and then the bottom one as a to actually switch power. Like if normally you see relays in order to switch power. Sometimes you see them switch signals. But then if I have a power down here, I'm switching it between on and off, then I can basically also get a little status bit that I run into a digital logic line that tells me if this relay switched. So that's ways you can use that. But oftentimes you'll just see these other ones for simple things. There's also something called a rotary switch. So that kind of has like a dial on it. So that may be the symbol for that. Okay, so let's see. So this is, so how do you draw these things? Okay, so there's a lot of free software out there. This actually could be updated. So Eagle is one that's pretty common. And with Eagle, you can do not only schematics, but you can also do board layouts. Express PCB must be another one, but some of the other ones that are free are like KiCad. That's one that's really popular right now. And that's, if you want a free one, then I would recommend that. If you want more advanced things, and particularly with your educational user ID or email, Altium, Altium is the one that I like to use, but that's what we use to design pretty complex boards. So it's not necessarily beginner friendly, but for those that are looking to do kind of more complex designs, it's a great place. It's an industry standard. And As of right now, you can get a free license with educational emails. You just have to ask them. So, okay, so what do we do? You know, how do we build this stuff once we've got the schematic, right? We've got a schematic designed. Okay, now I need to actually build this thing. And there's multiple ways you can use with like multiple steps of complexity. Okay, so the easiest one is what we call a breadboard. And so some of you will see this in your lab or maybe you've used this before. This is basically what the blank one looks like. And then you can go in and kind of start putting integrated circuit chips as well as these different wires and be able to hook things up. So I would say that before you just go start wiring things up on these things is to actually take your multimeter that you learned about last time and make sure that you understand how these rows are connected. So I can tell you that typically I guess in this orientation, this would be considered a column. So every column here on this side, not on this side, but on this side, each column is connected across. So it's like 1, 2, 3, 4, 5. There's 5 slots. Then this second one is not connected to the first one or the third one. It's got its own connection across the 5 slots. Okay. And then the same thing here. These are connected, but they're not connected to each other in the rows. And then typically you'll see these things and they'll be connected all the way across. So across a row, these are all connected. Usually you put your power here and that way you can kind of like distribute power and then you'll have all your signals here. Okay, and then you can like apparently get a piece of wood and hook things up too, which is what I think this is representing. So yeah, breadboard is a pretty good place to start. But you can see, I just want to point out that this is getting pretty complex here. And it's very easy to start to make mistakes whenever you're doing big boards with this. So, and if it's something that you're going to use in the long term, you want to, you know, do a little bit of prototyping with this, but ultimately you want to go to layout. So, and we'll keep moving across the way. So this is not a layout. This is a step up from the breadboard because in these are called perf boards or proto boards. And there's a lot of different types. A lot of them have very different connections. So you can look at that whenever you're starting out with this. But this will allow you to actually make solder connections on here. So you start to solder, and then this is a little bit more permanent than the breadboard, but it still can be a pain. I'll just say that. So yeah, but sometimes this is really quick and easy to get something implemented. So this is some other type of prototype board that I have never used anything like this, but this is apparently a Manhattan construction. So again, there's so much technology right now with being able to get printed circuit boards quickly. You know, you're going to spend a lot less time actually designing a board than creating this one as well. So, okay, so this is really the edge circuit boards. This is what I'm talking about. So whenever you hear the term PCB, that stands for printed circuit board. And usually, you know, these are 2 different types. You can see there's like, this one's blue, this one's green. You can get different colors. The most common color is this green one right here. Okay. And the most standard material is called FR4. And that's usually just pretty cheap. And so this is saying, you know, expensive in small quantities, $300 per board. There's a site that I like to use called Advanced Circuits. You can get $33 per board for a 2-layer board. And so typically when we're doing prototypes, we'll do that really fast. OSHA Park is another one you might see out there. They have purple boards too, which is kind of cool. You can do prototyping very quickly they have very fast turnarounds and it's pretty inexpensive. So I would recommend that, you know, that would be the way to go. So, and this is what, this is what we call a bare board, just means that it hasn't been populated, assembled, or soldered, however those words all kind of are interchangeable. And then this is one that looks like, you know, after it's been assembled, which is what eventually this is not a board we're using, but this is what one of your boards will kind of look like in the end after you finish assembling it. So prototyping with surface mounted devices. Okay, so we are not going to do this until next, I think next semester is whenever you start assembling your Megasat board. That's whenever you'll have to use surface mount components. So they're not quite as easy to work with as the through hole. So we're going to be starting with the through hole components, and then you'll be able to move on to this. So they are pretty small, but so it's really important though for you to understand the difference between a surface mount device and a through hole one. And that's because if you go to order parts, let's say that you need to go ahead and order a resistor, you go to DigiKey. DigiKey is a company that you would just order parts from. Then you need to make sure that you select a through hole part rather than a surface mount part, because the through hole part is, we're going to be working with it today, so you'll see it, but the surface mount component will not fit in the same board as a through hole. So very different. So it's important to know what you're ordering whenever you're ordering components, and then we'll learn more about this next semester. So whenever you have surface mount components, like it can be very hard to test. So this is an example of a surface mount component right here. And you can get breakout boards. So this is just telling you that, hey, there's ways that you can do some testing, quick testing with these things. Breakout boards are a great way. Sometimes you'll see this if you ever go to like a company like SparkFun. They have a lot of really cool, like a little electronic boards and development boards you can buy, and you'll see a lot of breakout boards with them. And this is the surface mount. This is one example of a resistor and capacitor. So it looks, these are very, very small. There's also different like sizes. So the 0603 is probably the smallest that you ever want to get. If you can get larger ones like the 0805 footprints or the 1206, you'll be a lot happier as a person soldering those than whenever you do the 0603. So you can go smaller than this to the 0402, but usually whenever you see those components, normally there's, you send that board off to an assembly company, and they use like pick and place robotic machines that will do all of the soldering for you. So, and then you just get the board back. So just keep that in mind. This is what it is. So multi-terminal, this is just for different types of surface mount devices. And this is more dealing with the integrated circuits. So there's different things you might see, small outline transistor. These are just different footprints, and small outline and SOIC, DFN, the ball grid array. By the way, if you see a ball grid array, you have to send that off to a company to solder it, because the leads are all underneath the device itself. So try to avoid those. Land grid array, ball grid array, don't get it unless you know you're going to send it off. Okay, so that's the end of